Okay, see, in this lecture, this hour, I am going to talk about controls fixed stability, which is same as actually straight line stability that we have talked earlier. If you remember, we have talked about this, that if a ship was disturbed then after that it may take another straight line or may not take. Now, what is this control fixed? Let me also explain that. See, I have this ship here, right. Now, by control fixed, or what I meant is that we are not applying radar. Radar is what is called control surface. You basically are looking only at the hull. Okay. Now, the question is that if I were to disturb the hull, will it take another straight line or will it go haywire? That was the question we asked earlier. Now, what we want to study today is that based on those hydrodynamic derivatives and equation of motion, what is it that is required to be satisfied to ensure that the hull has a control fixed stability. You see, I will tell you an analogy of that. Many of you are coming by bicycle. Now, you will know in some of the cycles which the wheels is not properly aligned, you have to continuously kind of steer it in order to make on a straight course. Some of them you will find out that it is much easier, like if some of you try to ride cycle without your hands, like without putting, you will find that if a cycle is very shaky type, like wheel is not aligned, very difficult to maintain straight line, you fall. But there are some cycles which you probably can more easily make a straight line. Basically, there is something that is there in the dynamics that characterizes these two. Like if you have your forward wheel is not aligned, it is kind of having a what you call is not exactly in the center plane, etc. Then it is more tough, you continuously apply your hand. So, similarly in the ship, see, now what one you prefer? Obviously, most people will prefer a cycle which has its inherent stability, because otherwise that you continuously monitor, it may be an effect on the radar. So, same thing applies for a ship. Yes, I could probably make it straight line by applying radar continuously, but I do not want to apply. I want to make sure that if I put the radar straight, it goes on a straight line. Even the small waves, etc., come, do not disturb it much, it maintains a straight line, which therefore means that I am looking for excuse me, a ship which probably has straight line stability. If not, I want to study what is it, how much it should have. So, therefore, that is what we are talking, and so unfortunately, we have to keep coming back to the equation of motion always, because that is what the starting point is. See, now let me just first write and then I will this thing. See, I had this equation, right, minus yv v, I quickly write this minus m yv dot, there is a purpose of writing that also, yr minus m. I believe this is yr minus m into u was there, this big U anyhow, r minus y r dot minus m x g r dot. This side is 0, and I had this this equation minus n v v. See, this becomes so elementary that every time we end up repeating it, right. But let me just quickly write it anyhow. Now, here see, I am going to this, what is this? You see, v dot is dv by dt, r dot is dr by dt. So, if you look at that, this equation is essentially a set of linear differential equation, but with two unknowns. In other words, I am going to rewrite that taking this, and then if I rewrite that, the equation will look like this: m minus yv dot d by dt minus yv v and actually what is, if you look at that, the equation part, for the front part also, what you will find out that this equation has a form something like that, something into V dot plus something into V plus something into R dot plus something into R equal to 0. There are two equations. In other words, the equation has a form like that. You agree with that, right? This is how it looks like. Something into V dot plus something into V plus something R dot plus something R equal to 0. Essentially it is, see, if you look at this, so this is nothing but two simultaneous linear differential equation, just like our this thing mx dot dot plus V or Bx dot equal to 0, something like that, just that it has no stiffness term right now here. Essentially it is two linear differential equation. So I am writing in this form, this way. Now you see why we are doing that, because you see when you do this also, what you do, you presume the solution to be something like x0 e power of sigma t, and then you substitute back and find out what is the value of sigma. That is what we have been doing it. That is the way of solving it. So you see, when I have this is a linear differential equation. This equation will have a solution that will look like, see, what I want to know from here again, when I look back at this, my purpose is to find out V and R with respect to time. I want to solve for V and R. So it is something V plus something R, something V plus something R, you can say, but of course it is differential equation because there is d by dt there. You agree with that? Now this is with the d by dt here. Had it been not there, it would be a simple algebra. But this is a differential equation. So how the solution will look like? Your solution will look like V will obviously because it is 2, you might have two these things, say V 1 e power of sigma 1 t general equation, because it is 2, there are two roots maybe there, and R will be R 1 e power of sigma 1 t plus R 2 e power of sigma, sorry, is E. This is a standard form of the solution, and all I need to know, I am not solving here. What I want to know is to find out the sigma 1, sigma 2 values. Now you see what is happening. Excuse me again. Very important. What do I want for stability? Suppose sigma 1 and sigma 2, any one of them is positive. Let us say real positive. What would happen? V and R will keep growing with time, which means the path is going to be going further and further deviated without a control. Suppose sigma 1, sigma 2 are imaginary number. If actually it's one imaginary, both will be imaginary because there will be quadratic equation. What is meant by e power of imaginary number? It is sinusoidal number. That means V and R will show it's going on an oscillation. What will cause me to make sure V and R become 0 with time? Only when sigma 1, sigma 2 are real negative numbers. Therefore, I need to find out what is it that makes sure my sigma 1, sigma 2 are real negative numbers. That will be my condition for stability. Okay, now let us look at what is sigma 1, sigma 2. Remember that this equation, I will go, you will have this notes later on, though you can see the equation. So this is like, I can call it this way, A1, and I call it this way, A2. See the A1 d by dt, A2 like that. I just want to write it so that you will know. I can call it say B1. I can call this with the minus sign, right. So that I have this thing. I can call this to be A3. I can call this to be A4. I can call this to be B. I can call this to be B4. Remember again, I have therefore an equation of a form which looks like, if I were to just trace it here and write it from here, I have A1 d by dt plus A2 v plus B1 d by dt plus B2 r equal to 0, A3 d by dt plus A4 v plus B3 d by dt plus B4 0. Okay. Or if I were to write, it will be something like A1 d by dt plus A2 B1 d by dt plus B2 A3 4 Now, the question is that, see, this sigma 1 sigma 2 essentially becomes the root, actually if you put this back here, you will find out, and I am not going through that, roots of a characteristic equation, see, given by a, when a, b, c are going to be nothing but, if I were to multiply that, the terms essentially a, b, c will be, if I have this matrix, this matrix, okay, then the term that will come as a into d by dt square plus b d by dt plus c equal to 0. In other words, what I mean, if I were to take this is the, I think you all know this is what is meant by the characteristic equation that you will be finding out in any differential equation solution course. If I were to cross product this one, this matrix, if I take this, determine basically this matrix, and if I expand that, I will have something into d square by dt square plus something into d by dt plus something equal to 0. So that is having a form of a d by dt square plus b d by dt plus c, because you know that when you took this part, essentially sigma square comes out. Okay. So this is a standard linear differential equation solution. That's how you do. You basically substitute back that here and expand that, and then this, because of this e power, you end up getting a quadratic equation in terms of sigma, and then solve for that for sigma values. So what I mean is that this is all standard. We are not going to be discussing how we solve it, numerous way of solving it, but I am not looking at the solution. Remember, I am looking at the roots of the root sigma and the condition of the sigma to be real negative. Now, what is sigma? Sigma is supposed to be the roots of this equation, a sigma square plus b sigma by c. What is a, b, c? That is, when I expand that, the terms proportional to d by dt square is a, etc. So if I expand that, for example, I will end up getting things like, see, if I will end up getting, in fact you can see that, or we will a1 b3 minus a3 b1 d square by dt square plus you will end up getting a1. Actually, if I were to look, it is difficult to see here, a1 b3 and a3 b1, these are d by dt square terms. a1 b4 plus a2 b3 minus a3 b2 minus a4 b1 will be the d by dt term. So, that is what we will be writing here. A1 B4, well, if we are A1 B4 plus A2 B3 minus A2 B3 minus A3 B2 minus A4 B1, right, that into d by dt, say, and finally we have plus A2 B4 minus A4 B2, right. Oh, A4 B2. So, you see now this is my A. We will write down what is ABC later on in a minute, but what I want to show is this thing. What is sigma 1 sigma 2 then? So, A sigma 1 square plus B. So, sigma 1 2 are minus B by A plus minus by 2, right, by 2, let us say, well, we can put half here, not by 2. Okay, this we all know. Now the question is, in this relation, first question, I want to make sure sigma 1 sigma 2 both are real negative. What are the condition? You will find out that two condition for number one is C by A must be 0. Why? Because you see, suppose C by A was less than 0, right. Let us assume C by A is less than 0, then this term is going to be positive, then this term is going to be more than B by A, because it is B by A plus something square root, B by A square plus something square root. You agree? See, this is B by A square plus some number, square root of that is going to be more than B by A. So, now minus B by A plus B by A plus something small. So, at least one root will become positive. Okay, that is one. So, therefore, this you understand. Now, number 2 is we find out that B by A of course has to be positive, because see, B by A is suppose negative. So, this becomes positive, etc., but this term will dominate here. So, what would happen is that this minus B by A plus minus something. So, if B by A was negative, then minus B by A minus something, because after all this is a square root term, and if this was less than 0, this would become imaginary term. So, what you end up getting is obviously that I must have both these conditions satisfied. That means, if I want to make sure my sigma 1 sigma 2 both are real negative, I must have C by A more than 0, B by A more than 0. Okay. Now comes the second question, A, B, C. Now we have to look back A, B, C and find out. This is where my last lecture comes in picture. A, B, C, are they positive, are they negative? Is C by A positive, negative, etc.? What is the criteria that we end up getting? So, we will look at that. So, this part we understand, right. Now, we will look at this part of A, B, C part. Now, you see, we have seen this A1, this terms all, A and B, B and C. Let us look one by one that, okay. So, my A is A1, B, what was this A was A1, B3 minus A3, B1. What is A1? Now, we will have to look back term by term, you know. A1 is M minus YV dot, right. Let's like just this term A1, then we can write all the terms of course here. Now let me write all the terms only here. A2 was minus yv. Then we will to find out A1, A2, A3, A xg minus nv dot, right. A4 was minus nv. B1, we will put these numbers, then we will understand that. M xg minus y r dot, B2 minus y r minus m u, B3 I z minus n r dot, and B4 minus n r minus m x g u. Okay. So, this is what we have got. Now, let us look at A. I will actually go to 1 or 2 and then I will leave it to you for the rest part, because you also have to do some. Now, you see this A1, what did you find last time? Yv dot is a large negative. So, minus yv dot is a large, in fact, it is same as m. So, it is very large. In fact, it is very large positive. A1. What is B3? Minus nr dot. What did I say last class? Very large positive. Remember, nr dot was very large negative. So, minus nr dot was very large positive. So, this becomes very large positive. What about B3? No, sorry, A3. A3, remember, xg can be plus minus because depends on which side, and but xg is a small number. Nv dot. Okay. What was it in last class? Cross coupled term. Small value, positive, negative. It is plus minus but small. Right. What is B1? No, sorry, A3. What is B1? Same thing. Yr dot is actually same as this because it is a same quantity. So, it is plus minus and small. What do I get? Large, large, small, small. Never mind the plus minus sign here. What do I get here? Always positive, right? It is going to be always positive. Okay. Now, I am going to leave it to you people to figure out exactly using the same analysis why B, the quantity B, which is given by what did I write? The B is given by wait now this. This is what it is, no, B, and I am going to leave it to you, as I said, to figure out from this analysis. Okay, you should do a little bit of exercise because in this particular part of course there is really very less numerics possible. It's more of an understanding. So, you work it out, you will find out that this is also will turn out for a shape will be always positive. Okay. Then what do I get? I had to have C by A always positive, V by A always positive. Now I find out that B is always positive, A is always positive. So this criteria is satisfied. So it among the two. Now come to that. A is always positive. What does it mean? What it leaves to me? It says then that C. Now the term C. In fact, that also I leave it to you. The C, the term C. Let me write down the term C here. Term C is, what was the term C? Always going. That is A to B4. This term, if you work it out, you will find out it is not very easy to say whether it will be always positive or not, because it is competing two terms which are of similar magnitude. So what it means is, I will write it down, this term, this full term, this term will turn out to be A2 B3. We will come to that. Let us write it down. This is basically A2 is minus YV, right? B4 is, what is B4? We have to write it down, A2 B4. From here, let us look at this. No, A2 is minus YV, B4 is this thing. So this minus becomes plus. So this is YV NR minus AM XGU. Okay, this minus A4 B2. A4 is minus NV again, B2 is minus. So this is minus plus minus NV into YR minus MU. I think that is how it is, right? Let us see this correctly, whether this is how it is. We just check this, right? This is rather just 1 second. Let me just write down one thing. Okay. This is basically this. See, we will come to that later on. This is the C part, right? It looks like that. So what it basically means, therefore, by looking at the condition, what I find out that this, therefore the condition reduces to the fact that this must be more than 0. C must be more than 0. So the condition reduces. Once again, if I were to look back at that, the condition reduces, since my requirement for directional stability is that both C by A and B by A should be more than 0, but now I found out that A and B are always positive for the hull, which means the condition, the requirement therefore becomes for me that C must be more than 0, right? Therefore my requirement is that C, which is given by this, must be more than 0. That means, but well, if I put back, that means I must have this more than 0, which basically means this more than 0. So you see, my condition of stability therefore turns out to be this. This is the condition. So you see here, the interesting point that we have now ended up getting is that I must have my hull so with the values YV, NV, YR, NR in such a way. Actually this is so important that I am going to write it again in a big way. This is what the condition is. Okay. This is minus only. See there, now the most important thing that comes out. You see here, I therefore have a condition saying that my hydrodynamic derivatives yv, nr, nv, yr, the velocity derivatives, all are velocity derivatives, right. Interestingly, I don't have a term arising because of added mass derivatives. What I said in last class, among these 4, yv dot nv, nv dot yr dot nr dot, I have only this the velocity derivative coming here, accelerations are not coming. So it must be such a way that this condition is satisfied. That is very important, or the criteria that has come out to be. Now you see, this means that whether the hull is directionally stable will depend therefore on the values of yv, nv, yr, nr. This is of course with dimension. I will right now go to the usual form of non-dimensionalization, because typically we write this in a non-dimensionalized form. I did not say that so far because I thought I will, it does not change the conclusion. So this is what we call, this C is what is called stability index, you may call stability criteria, various terms are used. That means, interestingly, supposing I want to tell, I am designing a hull, okay, see, take the case, I am designing a hull, I want to make sure the hull is stable, okay, then I have to ensure that this value is positive. Again there are design condition comes in. If I make it very positive, then it becomes so stable, like your very stiff cycle, that turning will require more effort. On the other hand, I also want to turn, therefore what I will do, I want to make it positive but not much positive. In other words, essentially this value, this minus that, how much is more than that, which is what I will come to the later on, is a measure of stability, and therefore we find out the measure of stability is fully connected to the hydrodynamic derivatives. You cannot say I will not study hydrodynamics in order to become find out hull is stable or not, because stability is primarily decided by interplay of the hull forces created. All these are hull forces created because of the flow past the hull. If you look yv, because the ship is going in the angle of attack, there is a y force created. Nv, because of the same thing. Okay, so you will understand this part. Now we will get back to that. Let me quickly go through a standard non-dimensionalized form that people do it normally. Now that's, I did not do that before, but normally what happened, all these coefficients, after all, if you write yv, nv, etc., suppose I took a model, okay, so I have y versus v, but if I have 20 times bigger ship or 100 times bigger ship, then y will be 20 times more, v will be like that. So dy dv will become scaled up. Difficult to understand, say added mass, yv dot, if it's 20,000 ton ship, it may have minus 18,000 ton, whereas 2 ton model minus 1.8 ton. So obviously you would like to represent them in a non-dimensional way. So let's use the standard non-dimensionals of derivatives. Then we will write C in a non-dimensional form. Not only derivatives and other quantities. Normally what you do non-dimensional, usually you use forward speed u, okay, length L. These are the one that is of course rho you will be using. These are the terms basically used in non-dimensionalization. Okay. Like for example, and all the non-dimensional terms are represented with a dash. Typically in maneuvering studies, the non-dimensional terms are always represented. The nomenclature that is used, standard nomenclature, is to put a dash on the term to show that the term is non-dimensional. In fact, maneuvering is all study of dash and dot. Dot will be the time derivative, dash is non-dimensionalization. So, this is written as m by rho L cube. Normally, as I say, L is used, V dot is used as V by, in fact, I can call it U, the forward speed, steady forward speed. This is dash, of course. Sorry, this is V. No. This is V dash. V dot dash is going to be V dot L by. Remember the T is taken with L and U. See. Normally non-dimensional you will be with what? M, L and T, right? Normally non-dimensionalization you will be the parameter fundamental thing of the fundamental 3 dimensions are M, L and T. That you agree, right? Now L is taken care of. M comes from rho, because rho is after all mass by length cube. So from rho this M comes in, and T comes from L, U is L by T. So here the non-dimensionalization are usually done with U, L, P, which actually involves all the 3 fundamental dimensions, how you are combining them. So the V dot becomes V dot L by U square. I Z dash will become L5, R dash will become well, V means actually this V is U. Oh, there's, yeah, V will not come here. Oh, this is all dash. Etc. Actually, of course, then also U, the forward speed U. This is actually let me call this not U, I will call it V, or that U means the actual total velocity. So V U, the forward velocity becomes U by U bar is become 1. What I will tell you what is U. See, this U is the velocity vector. U V, this part is u. Okay. So, obviously, for small value of v, see this small u, the forward velocity along x axis is this into cos alpha, and this is this into sin alpha, if alpha is the angle of attack. If you say, if for small angle of attack means small value of v, which is what we assumed, obviously sin alpha becomes alpha, cos alpha becomes 1. So, that is why it becomes this. So, that is why when I non dimensionalize these terms, like let me look back at these equations again. If you non dimensionalize this term, all that will happen, this will become dashes, and you will be able to, I will look at the yvv, you will find out that yvv will have a unit of force, because after all this should be having a unit of force. Yv dot v dot, you will have unit of force. Well, let me just explain that once from this expression. See, for example, yv into v, you will find out it is yv dash into rho by 2 L square v, and v is going to be v dash into v, which will be yv dash v dash into half rho L square v square. You will find this as a unit of force. Similarly, I will leave it to you to find out that yv dot v dot will be yv dot dash v dot dash into, this will have a unit of force. You can figure it out all if you want to do. It will be obviously half rho L square v square. If you see nv into v, same thing you will find out, but if you find nr into r, you will find out this will become nr dash r dash. Remember this moment, half rho L cube v square, because force into distance. You can figure it out yourself, you can check it, but the important point here is that you will find out that this mxg, and especially this term mxg u, u will become, the u dash is become 1, because you see u dash so as a result what happened, this term will become 1. This term, when you dash it, when I just want to show you here without having to write much, if I want to put dash, it will become all that dashes. Okay. Only thing is that this term will become 1, because u dash is 1. So, this will become dash, this will become 1. That is all, not much to like understand that. So, this is only just for the sake of telling, but let us look back at this expression here, that is in terms of non dimensional coefficient. So, if I were to term in terms of non dimensional coefficient, what will happen? In non dimensional form, C will become yv dash nr dash minus m dash xg dash, u become 1, remember, minus nv dash y r dash minus m dash must be equal to 0. This, if you see, will turn out to be an expression like that. This is same as saying, this is very important, or rather I will, let me write this and carry it back next page, n r dash minus m dash xg dash divided by y r dash minus m dash minus n v dash by y v dash more than 0. This will turn out to be the same as this. Okay. So, this I will repeat next phase. So, the criteria becomes n r dash minus m dash x g dash divided by y r dash minus m dash more than n v dash by y v dash. This is my criteria. Let us put some physics into it. let us look at this term. Take this shape. What we will do is a part where we will put, let us just put O at CG, so that I do not have this term, because it is up to us, we can always put that. So, if I put this xg 0, let me put the xg as 0. Let me put xg as 0 means this origin is at G. Okay. Now, let us look at this yv by nv. You see what is happening. Now, understand this is very interesting. I am having a ship moving. What is yv? Y force because of v. What is v? What is v dash? V dash is angle of attack. That means I am going along this direction. So, I have got u here, I have got v here, rather sorry, no, sorry, not this side, u here, I have got v here, this is my v, right. When I go on an angle of attack, I have a v here, right. Now, what happened? This is going to give me a force, some force is giving. So, it is going to give me, see, when I go there, this side the force is coming. Okay. There is also moment coming. So, the net force, never mind the direction, the net force and moment is going to be acting at some point, because what is happening? See, I am getting a moment NVV and a force YVV. A moment here, I am getting some moment, never mind the direction here, NVV, and I am getting a force here, whichever direction the force is, actually here maybe other direction, YVV. Now, you see here what is happening. This hull, I am getting, if I give a V, NV and YV tells me that I get a moment NVV, right, and I get a force, yeah, it can be other direction, whatever the diagram is done. So, my point is that if I wear a stick like ship here, there is a ship G here, I am getting an NVV here, and I am getting, let us say here, YVV, whichever way, or no, this is the opposite side I wrote, in fact, because these are all negative sides. In fact, I think I should discard that and write you this way, because see, remember, this is my positive axis. So, I am getting here an NVV and I am getting here a YVV. What does it mean? Essentially, it means an equivalent force acting here at a distance of NV by YV. Suppose there was a distance force YV force acting here. What would have happened? This force is equivalent to this force YVV, sorry, not YV. Okay, and also equal to this moment, because this into this distance, whether this distance is NB by YV. See, it is like is a basic kinematics, no? A force here F is equal to a force here into a moment of F into R, right. Do you understand that? See, if I have a force here acting, this is nothing but a force here and a moment about this point. Now, what we have here is the opposite. I have here for this hull a moment here NVV, that is what I have described, and a force here YVV, which is equivalent to a force acting at this point, just one force at a distance NV by YV. So, this point of action, is like you can call a center of pressure in pure yaw. That means, supposing my ship was yawing, having a V motion, then the hull would have experienced a force at this point, which is equal to a force here and a moment here. This distance, this is called a neutral point or in sway or neutral point, actually this is assumed, or center of pressure in pure sway, this particular point. So, we have just a few minutes time. So, what is happening if I were to now go back to this diagram? This is one point. Now, look back at this equation. This equation, I have here nr minus, well actually I did probably make this another equation, right, with here. I had nr by yr minus m must be more than this. Now nr by yr minus m dash, this term, if you look at this term in a similar way, or this full term becomes the center of pressure, so called, for pure yaw. See here this comes only for yaw motion, nr yr for yaw motion. So this term, this represents to me the distance from center of gravity, because I have discarded that distance from center of gravity of the point of action of force if the ship was having a pure sway, just v, this one. If it was only going with an angle of attack, no rotation, okay, then it will be at this distance from the CG, as I have explained here in the other diagram, that is, it is at this distance from the CG where my force acts, the total force act. Okay. Whereas this other term, this term would be that the distance where the force would act, if, or moment would act, if there was only yaw motion. So what the criteria tells, is that the center of pressure of pure yaw, that if I call this to be Cp sway, and if I call this to be Cp yaw, this must be ahead of this. That is what it says. Now you see, now suppose the ship is not stable. What means that this is less? How do I make it stable? How do I make it stable? I can make it stable by see yv, remember here again, yv is always negative. We have discussed that. And of course in this diagram, typically for ship, this distance typically for ships is about, you can say, 30% of the length. This is 50%, this is about 30% of the length. Typically for ships, not always. What it tells me is that, see, remember this forward side, that means if this is negative, this is also negative, typically for ships, So it is typically negative, this is negative, and now of course we know that this is always negative. That you have seen in my last lecture, you can look back at that. What we are finding out therefore is that typically for ship also this is negative. Yeah. The negative implies, if you look back, the forward part of the hull is dominating, forward part of the hull is dominating. Now supposing I want to make the ship stable, you know what I have to do? I have to make sure my aft becomes dominating. Basically I have to make NV dash, suppose NV was negative somewhere here, so this is a 0 value somewhere here, I have to make it less negative. Remember, NV I have to make less negative, going towards positive side. What it means? Go back to the last class, I have to make the stern, the aft part, more and more dominating. How do I do that? Add a skeg. That is exactly what we keep doing. There is a hull here, I want to make aft dominating. What I do? I add a skeg, S-K-E-G, or I add the forward part, or I can move the CG forward, other way around, this one. So CG forward will do the same thing. Now you understand why for a bow and arrow my CG is forward. Why feather? By feather I am adding skeg, dominating stern. By moving my iron on the front, I am making my CG move forward. Essentially I am trying to make this forward, so stern dominating, because I want to make sure this moves back there so that this criteria is satisfied. So you see there is a full reason now we understand from physics. So in design also if you have a problem you have to do that. Anyhow, I am going to stop it here, time is up for today's class. We will get back on this little bit and then carry on from here on to other topics. Okay. So with that I will stop, but this is very important because now you have an understanding that directional stability essentially is a playing around with hydrodynamic derivatives, which is nothing but the hydrodynamic characteristic of the hull, and you therefore cannot avoid hydrodynamic forces if you want to study, you want to make sure the ship is stable. So, with that I will end.